I'm looking at this problem with in terms of numerical models. So this is a string rate model, a compilation of GPS measurements and fault slip rates that basically shows that plate tectonics are broad and strong segments separated by narrow and weak deforming boundaries. So the question is, which is the main factors that can induce strain localization at this scale? The first one that we need to talk is thermostructure. That's, for example, responsible for the stabilization of cold areas, for example, cratons and fold and truss belts, mobile belts. It's the hot regions in between, for example, two cold domains. Another factor that we can talk about at strain localization this scale is grain size evolution, that I think tonight Jana will talk a little bit more about, that grain size evolution can permit the stabilization of strike slip vorticity and divergent and convergent boundaries. But in my thesis, I'm looking at third factor, which is the role of crystal perforating orientation in the upper mantle. So previous modules showed, for example, that if we have a heterogeneous anisotropic plate, that means that we have domains with different textures, we can induce strain localization in the upper mantle. And it's known that this process can be preserved for quite long time spans. So it potentially can be an important factor localizing the formation at this scale. This correlation between CPO, crystallographic perforating and strain localization can be nicely imaged by seismic anisotropy measurements. We use seismic anisotropy measurements in intraplate domains basically to map fossil fabric in the upper mantle. So here, for example, we have 1, 0, 0 of olivine, which is parallel to the tectonic fabric at really large scales. And the question that rises when we look at this correlation is, for example, there in the Eastern African rift, if strain localization is being controlled or partially controlled by mantle fabric. It's known that olivine is viscous anisotropy, as Lars tell us this a little bit this morning. So can we really measure this olivine viscous anisotropy and see if it can localize the formation at plate scale? First of all, to answer this question, we need to be able to quantify at rock scale which is the mechanical anisotropy induced by texture. So here I have a plot I have 3 textures with different CPO intensities, and I deform these 3 textures in shear and torsion parallel to the previous shear plane, and I deform afterwards in extension perpendicular to the previous shear plane. I'm not going details here. If you want to go in a little bit of details, we can have a look in my first paper of my thesis. So basically, if we have only dislocation creep playing a role, we can see that torsion parallel to the previous shear plane is in average a factor of 6 weaker in stress for a constant strain rate than tension perpendicular to the previous shear plane. If we consider additional mechanisms, as for example grain boundary related process or diffusion processes, this magnitude of viscous anisotropy is reduced to about 2. So can this viscous anisotropy in terms of stress be responsible for localization at plate scale? We can see that VPSC can model viscoplastic anisotropy at rock scale, but it's too time consuming in terms of computation to be directly implemented in geodynamical code, as tried before. So for doing that, we develop a parameterization. I will try to explain quickly what I've been doing this 2 years. So we consider a fossil shear zone in the upper mantle and a crystallograph periorientation coherent with this fossil strike slip fault or with this fossil shear zone. And then we calculate that using VPSC. And then we calculate the mechanical response for all possible solicitations using also VPSC. Then we have the wheeled surface relative to that olivine CPO. So that's in red are the second order VPSC, viscoplastic constant model, the predictions. And we fit these predictions using the Hill wheeled criteria, quite old criteria that works quite well. There's some works in metals using this already, but for geodynamics is a novelty of our work. And then after that we fit this wheeled surface, we get these 6 parameters that fit the Hill wheeled criteria. And then we construct our anisotropic viscosity tensor, here we call P. Then we implemented this parameterization in the geodynamical code ADELI. It was written in Montpellier in the 90s. It's a 3D finite element code. It's Lagrangian, and we solve for thermomechanical equations. And now we resolve our constitutive equation with P, our anisotropic viscosity tensor, constant, which means that there is no CPO evolution. That's fine for our models because we are applying quite small finite strengths that we believe that we don't have much texture evolution. So that's the geometry of the model. I apply compression to a model composed to a model of 1,100 kilometers long, 500 kilometers wide, and 120 kilometers depth. My model has a crust, which is isotropic elastoviscoplastic crust. That here I use a wet quartzite. And I have my upper mantle, which have 2 domains in my upper mantle. We have the upper mantle, I would say the surrounding upper mantle, an isotropic viscoelastic, where we implement our parameterization. That's why it's anisotropic. And I put a fossil shear zone. You can see that's all only in the mantle. That is coherent with the texture fossil strike slip shear zone of about 50 kilometers wide. So that is the texture that associated to this strike slip. So basically 100 is parallel to the foliation in the mantle, and 010 is perpendicular to it. And in my surrounding mantle, it's an isotropic, but I put a random texture, which means that the surrounding mantle is isotropic. In terms of boundary conditions here, I applied 25 degrees at the top, 1,200 degrees at the boundary, and lithospheric pressure conditions at lateral boundaries. And I fixed one lateral boundary, so I'm applying basically uniaxial compression to the model. I did that using a velocity of 3 centimeters per year, just to register. So the first geodynamic application that I will apply this parameterization is the case of linear belts of interplate seismicity. Here I showed 2 maps of the Eastern North American continent. In one I compiled the S-Kais splitting database, so basically show 100 axis of olivine, the fast axis. You can see how fully that here is quite in this direction. Here it changes a little bit, but it's roughly in this direction. Here it changes a little bit. Here it follows the tectonic structure. And when we look the seismicity, the interplate seismicity in the region, we have a quite nice correlated trends. There we have the seismicity also at a huge scale, that's 500 kilometers, so we have a kind of 1,000 kilometers long of seismicity occurring in a linear feature. And here, for example, that's an interesting aspect. When we turn here for this, is where our texture kind of turn, our texture in the mantle. So the question is, can linear seismicity be triggered by olivine-induced viscoplastic anisotropy in the upper mantle? That's the question that we will investigate in this my second paper. So the results now. So here, first of all, I test the effect of the mantle shear zone orientation. So I keep that texture that I showed before, quite strong texture. Here the G index is 12, it's quite strong. So it's 100 parallel to the fault shear zone, the strike of the fault shear zone. As I said, isotropic in the mantle, in the surroundings. The second invariant of the strain rate here shows that deformation only localizes in the upper mantle when the fossil shear zone is at 45 degrees of the compression axis. Here you can see it's actually delocalizing on the upper mantle. Here you already cannot see. The contrasting strain rate in the mantle of the surrounding in the fossil shear zone is about a factor of 20 strain rate. And in the crust, we can see that we transmit deformation to the crust is a factor about 12 between 15 in strain rate. Here, in this case, I'm testing basically this relation. This is a plot of the angle between 0, 1, 0 and my compression axis for a cube. That was the validation test that I did. So basically, we see that at 45 degrees, we have the weakest position. That's normalized stress for the isotropic behavior. So basically, I'm testing this for this case, this contrast. But it's not the maximum contrast that I can have. For example, if I have a mantle where I have O0, O10 parallel to the compression, and in the shear zone I have the texture at 45 degrees, I can have the largest amount of magnitude of mechanical anisotropy. That goes from 2 to 5. If I look in more detail here, what's happening with the shear zone at 45 degrees, here I have a plot time versus strain percentage. So we can see that deformation is mainly accommodated. That's the components of the strain tensor. That deformation in the mantle shear zone at 45 degrees is mainly being accommodated by shear parallel to the fossil fabric. It's shortening perpendicular to the fossil fabric. So basically, it's a transpressive region in the shear zone at 45 degrees. Here I tested the effect of weakening on the crustal faults. Here I started with that's the law. I started with a frictional angle of 30, and then after 1% of deformation, I changed the angle for 15, 10, and 5. That means that basically I'm keeping the faults active. It's like highly lubricated fault towards low angles. So I'm not really keeping this detail. I want to go to something more interesting, in my opinion. But basically, we see that at small initial final frictional angles, deformation localizes at the top of the mantle shear zone and keeps activating these faults. And we have hopefully higher strains. So what I want to show a little bit more interesting, in my opinion, is what about if I compare the contrast in strain rate of the strongly textured case and the isotropic case, the isotropic weakening case. So basically what I did here was I took the constitutive equation, is isotropic, so there is no P viscosity tensor, and I just decreased the viscosity parameter in the equation for 5, and times the contrasting viscosity between the external mantle and the fossil fabric. In general terms, we can see that there is no much difference, general terms. But if we look in more detail, here I plot again for the mantle shear zone. Here I'm comparing the strongly textured to the 10 times ISO weakened, time versus strain. So basically we can see that in the strongly textured case, we have a much stronger transpressive regime taking place. So the texture seems to induce a quite large shearing parallel to the fossil fabric, to the fossil shear zone. Here I plot a line, a profile of viscosity in the 3 models, in the upper part of the mantle here, to investigate, for example, which is the contrast and viscosity between external mantle and fossil fabric. We can see here that in the texture case, which is the black curves, it's a little bit scattered like that because I plot here node by node in the finite element model. So we can see that in the strongly textured case, we have a contrasting viscosity of about 6. It goes from the background to 24.2 to 23.7. In the 5 times case, it's kind of similar. It's just 0.1 in viscosity, so they're kind of same. And then for the 10 times ISO weakening, we have here kind of 1 order of magnitude in difference in viscosity in between the external mantle and the fossil fabric. I just remember that I jumped 1, so I'm gonna get back because I kind of like. We'll explain quickly. What about someone could argue that I'm using too strong textures? That's the case. Oh. Sorry, guys. Yeah. All right. So one could argue that I'm using too strong textures. That in fact I was using 12.7. It's quite strong texture. And if I reduce in half, for example, I use a 6.2 as a intensity of the fabric. So here I have a plot from Tomasi and Houches 2015 that they compile more than 600 peridotites, and they observed that the main CPO intensities, they vary from 20 in a few cases to most of them in between, I would say, 4 and 6. So I kind of approach the more likely CPO intensities. In this case here, I'm plotting weaker CPO against the strong CPO. I'm comparing 2, time against strain again. So we have for the most stronger CPO a more strong transpressive regime again when we use stronger textures. And in terms of the crust, no much difference can be seen in the crust. Here I show plasticity in percentage, basically to show that crustal shear zone are still being formed at the top of the mantle shear zone, even when I decrease the fabric 2 times. So it's still quite efficient strain localization mechanism, a factor to be. So gotta go back to final and represent that. So what about if I change the boundary conditions? Because we see that a shearing parallel to the fossil fabric seems to be a quite important mechanism, a kind of important component of the strain rate. So what about if I block this shearing? What happens? So basically I block the lateral boundaries, so no shearing is allowed. So here's the reference case in which I have the boundaries free to move. So what we can see is localization still occurs on the top of the shear zone, but it's less efficient and discontinuous than the case, and we have lithospheric pressure conditions. Here I've plot time versus strain for mantle shear zone and crust shear zone. We see that transpressive regime when lithospheric pressure condition is applied, when shear parallel to the fabric is allowed, is much stronger than when we have free slip at lateral and bottom at the lateral boundary. In the crust shear zone, there's an interesting effect that in the previous models, in the crust, the shear parallel to the crustal shear zone was dominant. In this case, is extrusion parallel to Z is the most important component in the deformation in the crust. So what is the perspective and future work of this? I'm kind of working there is 6 months from this data, so I still have loads of things to test. But I will explore more different fault geometries. I already did some tests. For example, down deep faults that we have 100 parallel to the dip of the fossil fabric, of the fossil shear zone. I need to test different crustal rheologies. For example, as I told you, I use wet quartzite rheology. It's a quite weak rheologist, but I need to still test fels granulite, mafic granulite rheologies, dry diabase, and also 2 crust models, because these ones have 1 crust model. And what I need to do in more detail is to look fault in natures. For example, we have in the eastern United States some really nice example like New Madrid shear zone, and look, for example, I forgot the name now. 1 second. Notice exactly fault mechanisms, focal mechanisms. I need to look focal mechanisms in more detail and compare with, for example, my components of deformation in the crust. If we can correlate focal mechanisms with our models, and also, for example, the Armorican shear zone in France that's highly seismic fault and is reactivating some Hercynian faults. So I need to look more in detail these natural examples.